don't have that. There we go. There's the title slide. Whoa. Okay, that's bright. Hey, thank you all for coming. The title of this talk changed a couple of hours ago, which was very exciting for me and the team. And so I'm glad you all found it in the catalog and made your way here to join me to talk about Aurora DSQL. I'm really hoping my voice makes the hour. That's I don't know why we can't hold this in a city with normal humidity. I don't know about you all, but I am infinitely thirsty. Anyway, so this morning, Matt announced Aurora DSQL. It's our newest database offering, and in this talk, I'm going to be talking about kind of getting started, architectures on Aurora DSQL, a little bit about what we built and why we built it, and then getting into a little bit of depth, because it's a 400-level talk, on our isolation and consistency model. Tomorrow, I'm doing another session where I'm going to dive deep on the internal architecture of Aurora DSQL, the architecture choices we made, and so on. But this one is about building your architectures on top of DSQL. But first, I wanted to start with a little bit of a personal story about how I got here. So in 2020, I was working in the Lambda team. We were doing some really cool things in the serverless compute space, helping out across the AWS compute business. And as I was talking to customers about that, which is one of my favorite things to do at work, I kept hearing the same story, right? Like, I kept hearing from customers that they wanted to build on relational databases. They wanted to use the power of SQL. They wanted to be able to bring their existing Postgres or SQL code, but it was difficult because AWS's existing database offerings were a rather poor fit for serverless, right? There was this impedance mismatch between them, and so I moved over to the databases organization in AWS, kind of shifted my career into a little bit of a previous mode of thinking about databases and data storage, and ended up talking to a whole lot of database customers who were saying that what they really wanted was a multi-region active-active database, which was something else that was missing from AWS's fairly rich database portfolio. And so, we found a team, grew a fantastic team of talented folks to build this product, which I've just been honored to work with. But this has been 4 years. We wrote the first version of this PRFAQ in January 2021, and so it's been a long journey to get here. And I'm just super excited today to share it with all of you and to see what you build on top of DSQL. So what is Aurora DSQL? Fundamentally, it is a relational SQL database that is optimized for transactional workloads. And by transactional workloads, we mean the kinds of things that run your service architectures, your microservice architectures, mobile backends, and so on. This is not a database that is optimized for analytics or data warehousing. We have other great options in the AWS portfolio for that. This is optimized for those transactional workloads, doing small reads and writes, generally 5, 10, or so on statements per transaction, relatively simple SQL, maybe a handful of joins. It is scalable, both up and down. And so when we talk about scalability at AWS, we often talk about up, right? This is perfect for applications that are huge, thousands, millions of transactions per second. But the truth is that relatively few of you in this room have applications of that scale. And if you don't, consider yourself lucky. It's less fun than it sounds. And so one of the things that we built into Aurora DSQL from the beginning is the ability to scale down, the ability to be the right size database for applications of all sizes, from a few transactions a day to millions of transactions a second and beyond. It is serverless. And this is a word that I'll admit we've abused a little bit at AWS over the years. But what I mean here is that an Aurora DSQL database is like a DynamoDB database, or it's like an S3 bucket, or like a Lambda function. There is no visible infrastructure for you to look at, worry about, monitor, patch, keep up to date, worry about compliance. All of that is fully built in under the covers. You go to the console or into the API or use the CLI. You create an Aurora DSQL database endpoint. You connect your application to that endpoint, and you never worry about the infrastructure again, beyond maybe changing your IAM policies, looking at your transactions to optimize your bill, and so on. It offers active-active and multi-region support. This is optional, by the way. As I go through this talk, I'm going to talk about both single-region and multi-region applications. But this is one of the most important parts for those large and critical applications. One of those most important parts of Aurora DSQL is it allows for architectures that are active-active, actively running in multiple regions at the same time without compromising on isolation, without compromising on consistency, without compromising on atomicity or durability or those other critical ACID properties. It is also Postgres compatible. That means you connect with the Postgres client. You can use the Postgres CLI. Most of your SQL code that you've written for Postgres will work in DSQL. I'm going to talk about some limitations on that. Some are because we have announced a preview today, and we're working on towards GA. But over time, what you should expect to see from us is that we cover almost all of the widely used Postgres surface area. And again, this was an important lesson for me from running the Lambda business for a long time, where we were very excited from the early days when we launched Lambda about customers building new applications. But it turns out that for many of you, building new applications isn't something you do an awful lot of. You have code that is your crown jewel of your business. In some cases, it is the only existent encoding of your business logic and business rules. You aren't just going to press Control-N or Command-N and rewrite that code because you just simply can't and can't afford to. And that's why compatibility with an existing database engine and compatibility with existing SQL features was so important to us. And finally, DSQL is built on our experience. We announced Aurora 10 years ago at reInvent 2014. Actually, the same reInvent, we announced Lambda. And we've been running Aurora for that entire time. We've been running DynamoDB for longer, RDS for longer, and large-scale serverless services since the beginning of the cloud. In fact, AWS started serverlessly, right? SQS and S3, which were the first two AWS services, which was actually first is a little bit controversial, by the way, were both serverless. And so this is based on our many years, decades of experience building large-scale systems. As you can see from my T-shirt, we're celebrating a decade of Aurora innovation. And so, this isn't starting new. This is built on our lessons from running Aurora in production for critical customers for more than a decade now. Okay, let's dive into architecture. Talk about building an application. And here I'm going to build a small, simple, single-region application. I'm going to get a little bit more complicated as the talk goes on. Here's the simplest architecture. Well, not quite the simplest, but a very simple architecture you could build on top of Aurora DSQL. You have DNS, so your customers can find your service. ALB, because it's a useful place to do things like terminate TLS. And then a single machine running your application. Talking to a regional DSQL endpoint, right? You've gone to the DSQL console, or you've used CloudFormation, or used the CLI to create a DSQL database, and your application is connecting to that database. So this is a very simple, and in some cases, in some ways, kind of naive architecture, right? There's not much going on here. We could get much more sophisticated. But what do we get out of this? Well, we can get hundreds or thousands or perhaps tens of thousands of requests a second, depending on how efficient that application is, depending on how much CPU each request takes in your application. If we hook up something like auto-scaling groups on that instance to detect when it is failed and replace it, we could get 99.9% or better availability. We get no data loss on failure. There's no single machine in this architecture whose failure would cause us to lose data or lose more than a few seconds or maybe a few minutes of availability if that single application box failed. And it's easy to add more boxes as your traffic increases. Because of those powerful semantics of SQL, because of concurrency control, because of transactions, you can scale this architecture out. And so the bottom line here is that this is a very simple and, again, kind of naive architecture, but it is an architecture that has actually some pretty fantastic end properties. 15 years ago, I couldn't have wished to build something this simple with such great properties. And this has been a goal for us as we've thought about the AWS database portfolio. We want to take complexity out of your architectures. We want to simplify your job as builders, as architects, as designers of systems by taking the hard parts of running a system, like the hard parts of making sure that data is durable and low latency and high availability and so on, into our services, allowing you to build simpler architectures with fewer moving pieces. But could we get even simpler? How about we use a Lambda function and Lambda function URLs? The combination of Lambda and DSQL here, they go together great. This is like chocolate and peanut butter. Allows thousands of requests a second, or much more. I tested this the other day, up to tens of thousands of requests a second, with just in some code that I typed into the Lambda console. This might be the simplest possible, multi-thousand requests a second architecture that is available. There's no infrastructure here to worry about. It is multi-AZ resilient. It's scalable. It's easy to monitor. It's easy to think about. It's easy to reason about the security. And there are very few moving pieces in this architecture. So again, this is us at AWS trying to take on the complexity of building your applications in services like Lambda, like Fargate, like EKS, that make it easy to deploy applications at scale, and then taking on the hard tasks of transactional relational database in DSQL. So this has been fun, these kind of naive architectures. What about something a little bit more complicated? As I said, a lot of your applications are more complex than this. Not many of us run applications that can fit into a Lambda function, right? Our businesses are more complex than that. Our needs are more complex than that. So let's go a little bit more complex here. Here what I've done is I've taken my application. This might be a single box, or it might be an application stack. It might be a whole microservice graph. And I've deployed it 3 times, once into each of 3 availability zones. I put a load balancer, like an ALB or an NLB in front of that, which is going to do health checking. It's going to balance load. It's going to send the right load to the right places. DNS in front of that for my customers to connect to. And again, that regional DSQL endpoint. So what kinds of properties can I get out of this architecture? Well, thousands of requests a second, or much, much more, right? 99.95% availability. The ability to survive the failure or disconnection of an entire availability zone with essentially no customer impact. And then the infrastructure needs and how much management you have depends on your application stack and how you've built that application stack. And so that could vary between being very simple if you've built out in Lambda functions or Fargate or one of these higher level services, to being much more sophisticated if your application's needs require that. And so again, what we've tried to do here is provide really great end user properties, that availability, that scalability, the latency, and I'll talk more about latency as we go, for rather simple architectures by taking on the hard database needs like availability zone fault tolerance, like detecting when things fail, like scalability inside the database service. You don't have to worry about that with DSQL at all. So what's the trade-off? Well, as with all things, there are some pros and cons, some things you need to think about. And especially with scalability, you need to think a little bit about some patterns that will allow your application to scale. So here I'm going to give you one tip for scalability, and this is the single most important thing to keep in mind as you scale applications on DSQL, is to avoid hot write keys. And so here's an example of a SQL query or a SQL statement. This could be on its own as an auto commit, or it could be part of a larger transaction. And here what I'm doing is I'm saying, every time I see a poodle, I'm going to count up, right? And then I'm going to return that count. Very simple piece of SQL. And so the key that we're selecting here, the row that we're selecting out of this database to update, is based on this type of poodle. And this is the one that if I see lots and lots of poodles, right, I go to the poodle show, right, and I see thousands of poodles a second, this is where I could run into scalability concerns. And so if I have two concurrent transactions, two transactions running at the same time, right, one began, the other began, they ran the SQL, they run for some amount of time, and then they commit. The first one will work, it will commit, right? There's no contention because it is the first transaction that has tried to change that row, and that row hasn't changed since it read it. And we'll get into what that means as we talk about isolation in a little bit more depth. The second of those two concurrent transactions will come to try and commit, and it will get rejected. The database will say, no, you've tried to write a row that has been written by another concurrent transaction. Your commit is going to fail with an optimistic concurrency control error. And then what your application needs to do is go back up to the beginning of this transaction, rerun the transaction, rerun your business logic that ran inside this transaction, and hopefully commit it the second time. And so this is the single most important thing you need to think about as you scale applications, is watch out for those commits that say, I can't commit this because I found contention. But this is only true in cases where there are actually conflicting writes, right? And so here I have two transactions that are updating the same table, but they're updating different rows of the table. And because the type here is different, right? One of them I'm counting poodles, and the other I'm counting golden retrievers, this is going to be fine. Both of these transactions will commit perfectly happily. And so the lesson here is that you need to think about designing your schema in a way that spreads out updates and writes over multiple keys. The right number of keys depends on the target scale of your application, right? If your application is seeing a few requests an hour, yeah, don't worry about it. You can have everything in a single row. If you're trying to get to millions of requests a second, you're going to need to think carefully about the way that you design your schema to avoid having rows that are concurrently updated, not for correctness reasons. The database will always make sure that the right thing happens from a correctness perspective, but for scalability reasons. One way to do that is to choose keys in queries like this in your updates that are finer grained, right? There are many poodles in the world, but there aren't quite as many dogs called snuffles. And so if you use something like the dog's name or its UUID, my dog has a UUID. I don't know if yours does. You should give it one. It's useful. Then you're not going to run into these kinds of problems. And so again, this is kind of schema design issue. But this is very specific to writes. And here you can see that I'm selecting from these two, from the table, selecting the same row in two concurrent transactions. These two transactions in DSQL will never contend. They will always both commit, and what's more is one cannot slow down the other. They won't, they won't contend for resources, they won't contend for concurrency control. They will always commit, and it doesn't matter how many keys you read. And so that's kind of the end of my scale tip is, avoid hot write keys. If you're scaling up, the more you try and scale up, the more you're going to have to avoid hot write keys. Reads never conflict. And that's true of reads in read-only transactions, but also true of reads in read-write transactions. It's true of the reads behind an update. Writes to different keys never conflict. Writes to the same key from concurrent transactions can conflict. And then finally, the final property is that read-only transactions in DSQL always commit. They never get OCC failed for the reason of their first statement, which is reads never conflict. And if it's a read-only transaction, then that can't happen. And so between concurrent transactions, read-read conflicts, two transactions that read the same data do not conflict. That is okay. Write-read conflicts. One transaction writing a piece of data that another transaction reads never conflicts, and that's okay. Read-write conflicts, the kind of flip of that situation, never conflict, and that's okay. So those first three cases will never cause a transaction to abort. The final case is write-write conflicts. This is the case where two concurrent transactions are writing the same row. And that one will cause at least the second transaction of that concurrent set to roll back. My second scale tip as you think about scaling out is to avoid hot key ranges. And this is a little bit of a weird one. For folks like me who are very familiar with kind of more traditional relational database designs, whether that is Aurora Postgres or RDS Postgres, or you're running your own database instance, traditional database engines love data locality from a performance perspective, right? So they love having a small working set of hot rows. And the reason they love that is because that means they can keep those rows in their cache. They never need to read from their storage. They never miss that cache, and they can offer you fantastic performance. And so a lot of the kind of performance tuning of single machine databases is about optimizing for better data locality. And in a kind of computer science sense, data locality is just a great thing in single systems for performance. DSQL, on the other hand, from a performance perspective, loves dispersion. It wants your workload, especially your writes, spread out over the key space just as much as possible. And so from an optimal scale perspective, you can try to load each piece of the key space about equally. And again, how much this matters really depends on that target scale of your application. If you're talking tens, hundreds, maybe low thousands of requests a second, you don't need to worry about this. Just write things in the most natural way. If you're going up for millions of requests a second, you're going to have to pay careful attention to the way that your workload is spread out through your key space. One very natural way to do that, if you can, is to pick things like version 7 UUIDs as primary keys, which will often fairly naturally spread out a workload across a key space. And so this doesn't necessarily mean that you have to do something that is difficult or artificial. Okay, so let's get back into architecture and talk a multi-region active-active application. And I'll get into the talk a little bit later about why we like active-active so much. But fundamentally, multi-region here can be about two things. It can be about latency, especially read latency, for local clients and optimizing for the experience of clients. For example, you want your clients on the East Coast to have local read latency, your clients on the West Coast have local read latency to their data. And so you might want to spread your database out across the continent. And the other reason that folks will pick a multi-region architecture is for applications with really critical availability, resilience, or compliance needs. And at least some of you in this room who have compliance regimes that are requiring multi-region, requiring applications to be spread out across multiple AWS regions. So this multi-region active-active application architecture is going to have to be really complex, right? Like there must be a lot going on here. Well, no. What I've done is I've taken my multi-AZ single region architecture and I've just stamped it out twice. I've stamped one out in region A. I've stamped one out in region B. They don't need to talk to each other. They don't need to think about each other. They don't even necessarily need to know about each other. What you've done is you've gone to the DSQL console. You've created a DSQL linked cluster, which is what we call a multi-region DSQL cluster. What that's going to do is it's going to give you a pair of endpoints, a region A endpoint and a region B endpoint. You're going to point the region A application at the region A endpoint, the region B application at the region B endpoint. And beyond that, you basically don't have to worry about that other than stamping out that application, stamping out your management architecture, and so on multiple times. So let's talk about the properties that we get from this architecture by talking about failures. What happens in this architecture if we lose an availability zone? It gets disconnected, power fails, natural disaster, whatever reason. And actually, the much more likely reasons, by the way, are you messed up a software deployment, one of your operators terminated the wrong box, right? Like that stuff happens way more often than the natural disasters, unless you're super careful. So what's the availability impact of that? Well, your load balancer is going to need to figure out how to stop sending customer traffic to the bad application. So that might take seconds. DSQL is going to do the right thing within milliseconds, remaining available in the two remaining availability zones in that region constantly throughout. There will be no data loss, no loss of durability whatsoever. No committed transactions will disappear. There will be no consistency loss, right? Again, there will be no time when you see weird time moving backwards or anything like that. And depending on how good your application architecture is from a health checking and load balancing perspective, the availability impact to some customers could be as short as milliseconds. And so even with this relatively simple application architecture, what we can get is an application that has, potentially milliseconds of downtime, even in the case of a major infrastructure failure, or even in the case of a major operational mistake. And that is a huge advantage. Now, I didn't even want to build the next slide. It scares me. I don't like thinking about it. But I do have to think about it. And that is what happens if you lose an entire region. Well, let's be nice and say we're going to lose this entire region because of an operational mistake, because of an expired credential or something like that, because you did a deployment of bad software. This could also be because of natural disasters, loss of connectivity in the backbone, and so on. Again, those things are rare, but you need to plan for them for the most resilient applications. You lose an entire region. How would this have worked before DSQL, before an active-active architecture? Well, what you would need to do if you lost your primary region is figure out how to fail over onto the secondary region. You're going to blow the dust off that application, which might not have seen traffic for weeks or months. You're going to really hope that it still works, despite not having done much for a long time, maybe not have been maintained correctly. You're going to flip your database over, which can be really easy. It can be difficult, depending on the nature of the failure. And you're going to see, potentially minutes, hours of downtime. With an active-active architecture and DSQL, the downtime, even in this disaster scenario, could be as short as milliseconds. DSQL will detect this case, and tomorrow I will go into details of exactly how this will work. It will remain available in region B throughout. It will remain strongly consistent in region B throughout. It won't lose any data, so no committed transactions will disappear from the system. And you can, again, even in this real kind of disaster scenario case, have very short amounts of downtime. So I keep going on about active-active. Why might I prefer active-active? Well, there are a whole bunch of reasons. And again, this really comes down to us learning from our experience in running AWS, running large-scale applications for a decade or more. And those lessons keep telling us that active failover architectures are hard to get right. It doesn't mean they're always the wrong choice. It just means that they are architecturally difficult. I prefer active-active architectures. It means that both sides are continuously working. And so you know both sides of your application are working because they are taking traffic, because you can monitor them in situ, show that they're working every second of every day. Caches stay full. JITs stay warm, right? These aren't applications that have been sitting quiescing for days or months. It makes capacity planning and forecasting easier, again, because you're running the whole time. You're gathering continuous operational experience across multiple regions, across both halves of this architecture. It gives you the option, and I'll talk about why this is so cool in a second, to route customers to the closest region and offer them better latency for both their reads and their writes. And that's cool because DSQL offers symmetric latency. The latency is the same on both sides. That endpoint A and endpoint B will offer you the same latency experience. And that's quite different from some other distributed SQL products where there is a primary region which is fast and a secondary region which is sometimes kind of arbitrarily slow. And so I prefer, when building multi-region applications, to choose active-active the vast majority of the time. It seems at some level like you might look at it and say, well, that sounds more complex. But because you can hand off the really difficult task of concurrency control and consistency to the database, it really simplifies the rest of your application by knowing that it actually works on both sides. Okay, so let's talk about that symmetric latency and talk about why it's so interesting to be able to route customers to their closest region when you're building a multi-region application. In DSQL, reads are always in region. They're always fast and in region on both sides. And so when your application in region A talks to its endpoint in region B, its SQL will be executed in region A talks to its endpoint in region A. Its SQL will be executed in region A. It will get data from a storage node in region A. In fact, in the same availability zone it's running the SQL in, by the way. And will never have to reach out across the continent potentially, across the world potentially for read data. So your begin is fast, local, in region. These selects, they're fast, they're local, they're in region. Your commit, fast, local, in region, does not require reaching out over the continent or coordinating at all with the other end of the database. And because a lot of transactional applications are read-heavy with a majority of read-only transactions, this is a really great optimization opportunity. Why are there so many read-only transactions? Well, because, imagine you're like building Amazon.com, right? Like a customer comes to the application, they browse the catalog, that's a read-only thing. They look at product detail pages, that's a read-only thing. And only when they come to making a purchasing decision to put something in their cart, which is more infrequent, do you need to do writes. And a lot of applications, a lot of web applications, a lot of mobile applications, a lot of service architectures have very similar patterns. And so taking advantage of these fast reads is super useful. So here's the surprising thing. This is where some of the distributed systems folks in the room might be thinking, what's going on here? Turns out that writes are also in region. They're also fast, they're also local, and they also never reach out across regions. And so here I have a transaction where I am doing a begin, start transaction. I'm doing an update, I'm doing another update. These are happening from the application in region A to the endpoint in region A, SQL's running in region A, the reads that are used for this update, because an update's a read, modify, write, coming from region A, nice and fast. Even in read-write transactions, the selects are still fast and local. And so you can have mixed mode transactions that do both reads and writes without losing this cool locality property. And again, this is happening because all of these operations can happen in that region with strong consistency. And the reason they can happen in that region with strong consistency is because of this investment that Matt talked about this morning in building out our multi-region clock architecture, in building out the EC2 time service that distributes very high accuracy clock signals to every EC2 instance around the world. And you can use that in your own applications, by the way. This isn't something we built only for Aurora, something you can take advantage of in your own stuff today in EC2. It's available to you. And so here we can see that the reads and writes are happening locally in region. The reads are going to local storage, and nothing has to cross that chasm, that long latency chasm that might cross a continent or cross the world. And so when do we pay? When do we pay for this? Well, we pay a commit time is the answer. Commits cross regions because they have to cross regions. And this is the law of physics that we run into, right? We can't tell you that if we lose a region, you don't lose data unless we synchronously make that data available in both regions or in multiple regions at commit time, before that commit returns to the client. There is no way of doing better than this. You just have to do it, right? It is the game. So how, when I say slower, how much do I mean? Well, I mean about 15 to 100 milliseconds, depending on region configuration at commit time. And so if you look at the region configuration, we support for the preview that you can try out now. That is in US East 1. It's in US East 2 with what we call a witness region in US West 2. And that you'll see commit latencies in the multi-region mode of around 20 milliseconds. So you could typically expect a single update like this to take 3 to 5 milliseconds, maybe a little bit faster depending. You can expect a trivial select to take something on the order of 1, 2, maybe 3 milliseconds. And then you'll come to the commit, and the commit will take kind of 15-ish to 20 milliseconds, maybe 100, depending on how you've set up your multi-region cluster. And so this leads to another surprising thing that sometimes surprises database folks and distributed systems folks, is that in DSQL, transactions improve latency. Right, like a lot of people, you come out of thinking about distributed systems with this idea that transactions are a slow concept that slows things down. But in DSQL, because we can amortize the cost of all of that cross-region coordination across all of the statements in a transaction, writing transactions with multiple statements improves your latency. It improves your throughput. And so within reason, within the constraints of your application, you want to write transactions that do multiple things. I wouldn't say quite as many as possible, but try and amortize multiple units of work across commits. Right? If you're doing auto commit or equivalent, you probably aren't getting the best latency experience out of DSQL. And again, read only if you can. Don't write to the database unless you need to. Because remember those read-only transactions, they're always fast, they're always local. Even on commit time, you never pay a cross-region coordination penalty. The huge caveat to making big transactions is going back to conflicts. The more keys you put into a transaction, the more likely it is that that transaction is going to conflict with another concurrent transaction just because there are more keys. There are more opportunities to conflict. And so here you can see some simulation results where I have compared for two distributions of key heat, the sort of zip distribution, which is very hot on the kind of head of the distribution, and a uniform distribution where I've spread out the load across the key space. And I've looked at the probability of the second of two concurrent transactions conflicting depending on what percentage of the keys in the database your transaction is accessing, right? And so here we can see at 1%, 1 in every 100 keys in the database, with a zip distribution where you've got a lot of hot keys, the chances of those conflicts is fairly high. With uniform distribution, they sort of trended up towards 50% when we've gotten to this point where we're accessing 1% of the keys in the database. So this seems dire, right? Like this seems like, oh no, this is a problem. But honestly, how often do you write transactions in write transactions in a transactional application that accesses or writes to 1% of the keys in the database? Well, actually pretty seldom, right? You probably have thousands of customers. If you're lucky, you have tens of thousands or millions or billions of customers, right? Your data sizes are very, very big. And so unless you have designed your schema or your application in such a way that it is very skewed in the key space, you're unlikely to run into this style of problem. It is something worth being aware of, though. So in our last 15 minutes or so, I wanted to take a little bit of a deep dive into isolation and consistency. So I've talked a lot about consistency. I've talked a bit about isolation during this talk. And here by isolation, I mean the I in ACID. This is kind of the isolation level that database folks are familiar with. And by consistency, I mean the distributed systems definition of that, not the C in ACID. And that means, do I read my own writes? Do I see other transactions' effects at the right time? Do transactions appear to be ordered correctly, and so on? So let's dive into that. DSQL in our preview mode offers a single isolation level. This is an isolation level called snapshot isolation. It's a fairly strong isolation level. In fact, at least one famous database provider calls this level serializable. Makes database academics real mad, but doesn't seem like anybody else is particularly worried about that. But this is our chosen isolation level that we're supporting for the preview, and I'll get into why we chose that in a second. So how do we do this? So each DSQL transaction, well, actually, no, sorry, not how do we do this, what are the properties of this? Each DSQL transaction commits atomically at a time, this time t. And so atomically means it all happens or it all doesn't happen. It appears to all happen at a single point in time. It is visible. All of its effects are visible to all transactions that start after time t, and is invisible. None of its effects are visible to transactions that start before time t. Transactions that abort or roll back are never visible to other transactions in this system. In-flight, pre-commit transactions, those transactions where you've done writes, you've made some changes, but you haven't called commit yet, are never visible to other transactions in DSQL. They are fully isolated from other transactions. And so far, this sounds serializable-ish, right? Like, transactions are atomic, they happen at a single time, you don't see newer transactions, you see all old transactions. What's going on? Well, a transaction that starts at time t, and here I'm saying starts and not commits, and so this is a slightly different concept. A transaction that starts at time t sees a snapshot of the database, a fully consistent snapshot of the database at that time t. It sees all the transactions that were committed before t, it sees no transactions that were committed after t, and it sees no in-flight or aborted transactions. And so here we have two concepts. We have the commit time of a transaction, which is the time that your transaction gets written to the database. And then we have the start time of the transaction, which is generally the time that you call begin or start transaction. And between those two is this period of conflict where you can read keys that another transaction that goes on to commit writes. And this is what fundamentally makes snapshot isolation non-serializable. And And there's some really great examples of this. Explaining isolation levels is super hard, and so I'm not really going to go into a lot of examples, but there's some fantastic kind of material on this online. The other thing DSQL is strongly consistent, even in the multi-region mode. And specifically what we mean there for the distributed systems people is that it is linearizable. Every transaction appears to happen, as I said, atomically at a certain time t. That time that a transaction happens atomically is, and by happen I mean commit, that time that it happens atomically is definitely after the time, the real wall clock time that you started commit, and definitely before the real wall clock time that you got a response to your commit. And so those things don't happen instantaneously, right? This is a distributed system, and so there is some period of time between those. But that atomic moment of commitment always appears between the start of your commit and the end of your commit. And so this is this really strong consistency property called linearizability. And the upshot of this is that if you do a write to the database, and then you tell somebody else that you've committed, they will always see the impact of that write. Or if you do a write to the database and then you do a read immediately after, you will always immediately see an impact to that write, even if you do, or the effects of that write, even if you do that write in a different region. And so this is a very strong consistency property. And so putting these things together means that DSQL offers what the literature calls strong snapshot isolation. It's a combination of snapshot isolation and strong consistency or linearizability. And for most applications, this provides a really simple programming model where your developers don't need to worry about the distributed nature of the system. And again, this is us learning from decades of running AWS services. We've found that developers find it very difficult to write correct application code in the face of eventual consistency. And this is a bit of a turnaround for AWS and for Amazon, right? We started as one of the big proponents of of eventual consistency. 15, 20 years ago, we were talking about all of the scale benefits of eventual consistency. And what we found as we built some of the world's largest applications and some really complex business logic applications is that application programmers just find it super hard, sometimes impossible, to write correct code in the face of eventual consistency. And so we have chosen strong consistency for DSQL by default right now as its only mode because we think that is such an important lesson that we've baked into the service. So if you're familiar with other databases, you might be wondering where our isolation level, this one we're calling strong snapshot isolation, fits in the whole spectrum of isolation levels offered by different databases. MySQL read committed, Postgres read committed, and MySQL repeatable read are all strictly weaker isolation levels than the isolation level that we offer in DSQL. Postgres' serializable mode, which is truly serializable, is a stronger isolation level than the level that we offer in DSQL. And our isolation level is equivalent to Postgres' repeatable read mode. There's also something that's a little bit controversial in the database community. Postgres repeatable read is not implemented the way that ANSI says. It's implemented using snapshots, and so is actually kind of not strictly repeatable read. It's just better. Postgres did the right thing. It's just not the right thing that the SQL spec says it should have done. It's a common thing with Postgres. Postgres does the right thing a lot. I really appreciate it. Designed by smart people, I think, is part of that. So why strong snapshot isolation, right? Why not serializability, or why not a weaker level? Well, this is because we think that for distributed large-scale applications, or applications of all sizes, strong snapshot isolation is something of a sweet spot in the trade-off space. I spoke about the benefits of strong consistency. Again, those are all about making it easier for application programmers to build correct code, to write applications that actually work and actually do the things that those applications are intended to do, and that's super valuable. So why snapshot? Why not serializable? Well, serializable is actually, I mean, at some level it sounds better, right? Like, hey, I don't have to ever worry about transaction anomalies. All of my transactions are going to be lined up in time. The world is just going to be so pure and so nice to me. But folks who've been around the database industry for a while know that serializability comes with some pretty big performance downsides. And those are performance downsides that push complexity onto the application programmer, because application programmers need to write their queries and write their applications in a way that doesn't fall into the pit of serializable performance problems. And specifically, because serializable requires you to look at the set of reads that a transaction does and compares that to writes that other transactions have done, it requires you to write code that is very careful about how many rows it reads in a transaction to get good performance and good scalability. And so while serializability sounds like a great idea, and in some ways it is a great idea, it is also something that adds a bunch of complexity into application programmers' lives. So then why not weaker than snapshot isolation? Why not like, read committed or read uncommitted or just no isolation at all? Well, it turns out that in our architecture, because of the benefits we get from the way that our storage works, and I'm going to talk about that in detail tomorrow if you're interested, we use a technique called multi-version concurrency control combined with those hardware clocks that we have. It turns out that we actually get no performance benefit from weaker isolation levels in our architecture. It also turns out that if you are building a scale-out SQL layer, the way that you achieve scale as you scale out that compute layer is by having all of the individual components of that compute layer not talk to each other. Fundamentally, the way that distributed systems scale is by avoiding coordination. And if you have multiple things running SQL, a horizontally scalable fleet of things running SQL, you don't want them talking to each other mid-transaction, because that's just more coordination. And if they don't talk to each other mid-transaction, well, there's no way for uncommitted effects to become visible to other transactions, because they're happening completely independently in completely independent spaces. And so in a lot of ways, we get a big isolation benefit almost for free because we've designed for scalability at that layer, for reducing coordination, reducing the number of messages that fly around the system when you are running transactions. And that is a very big scalability benefit, it's a big availability benefit, it's a big latency benefit, it's got all kinds of other good things. And so it's nice to get kind of a little bit of isolation benefit also for free out of making that decision. And so we think that for distributed systems, strong snapshot isolation is a sweet spot. It's somewhat of the ideal kind of isolation level, the ideal set of trade-offs. I think over time you might see us support other levels. We might end up doing serializable if there's demand for it from folks who run their databases at that level, which relatively few people do, by the way. And so we're not saying, hey, this is the only thing we're ever going to do. We are saying we chose it because we think it is a really good default for the kinds of applications that we think our customers are going to build on Aurora DSQL. So what have we learned over the course of this talk? Hopefully you learned something. I haven't just talked for an hour for no reason. Simple architectures can scale well too. Simple architectures can have great availability too. They can have great durability properties. They can have all kinds of really nice properties if you can get a database like Aurora DSQL, or like DynamoDB, by the way, which handles a lot of the failure tolerance, multi-AZ, durability, and so on for you. And this is a huge benefit of running against a cloud database, is it allows you to get great properties out of simpler architectures. We learned that active-active is good. It's not the only way to design multi-region applications or multi-AZ applications, but I think it's a really good default. I think it's a really good default choice for folks. And what's so interesting to me about this point is that if I say to folks, hey, you're going to build across multiple availability zones, you're going to build across multiple data centers, almost nobody is going to do that in a kind of active failover kind of way, right? You're going to do it active-active. You're going to lay out your application across multiple availability zones. You're going to have them all talk to the database, and your application is going to run in that mode. And why do you do that? Because it simplifies things, because it lets you spread out the work, because it lets things, be more resilient, because you don't have to worry about failover. And so all of those same reasons you would choose that as a multi-AZ architecture apply to multi-region architectures if your database is great at active-active across regions, which we have designed Aurora DSQL to be. We've learned that one of the important things for scalability is avoiding hot write keys. Probably the single most important thing for scalability on Aurora DSQL. Again, as I said earlier, if your application is doing 10 requests a day, yeah, you don't have to worry about this. It's not a big deal. Just do whatever. But if you're trying to get into kind of millions of requests a second or hundreds of thousands of requests a second, you're going to have to design things quite carefully to avoid hot write keys, get great throughput and great scalability up at that end. We learned that you should use transactions. It's potentially a little bit surprising for folks that transactions can make things faster and more scalable, lower latency and higher throughput. But they're a great tool. They're a great tool for application developers. They make writing concurrent code much easier and cleaner. They make writing fault-tolerant code much easier and cleaner because if you have failures, you can just roll back. And in DSQL, they can improve your performance, which is just super great. So if you would like to learn more about DSQL, we've gotten most of the documentation up now. There was had a bit of some false starts there. But you can check out stuff online. But there are also some really great talks coming up. Tomorrow in DAT427, I'm going to talk about the internals of DSQL, what we designed and how we designed it, how we built this thing, and the pieces of it that we think are powerful and interesting and unique. 421 is a hands-on DSQL workshop. We're going to be actually building an application on DSQL, getting from 0 to 1, seeing how that works. I love those hands-on workshops as learning opportunities because you actually get to see not the theory that I've been waving my hands about, but the actual reality of what it takes to build things. And then 334, we have one of our Ps, James, and the product manager who's been with us for this whole journey, doing a chalk talk, answering your questions, kind of going to sketch out on the board, architectural choices, different ways you can structure schemas, some of the features of DSQL. And so that should be a really great talk too, if you would like to have a bunch of kind of question and answer time with some folks who are just super deep on this service. Well, thank you very much. Again, I'm Mark Brooker. You can reach out to me at my work address. I'm on social media. Reach out on LinkedIn, however you want to. Please go out and try DSQL. It's in the console. We've got the tools. You can use your Postgres driver. You can use your favorite Postgres CLI. Give it a try. Tell us what you think. Tell us what features you would love us to build next. Tell us which of these things that we've done you think are great and you're happy with. Tell us what you should change. The whole reason that we're going preview before we offer a GA is to get feedback from customers like you, right? You're at a 400 session. I assume you're quite sophisticated. You're an expert on this stuff. And you are the kind of people who we would really like to hear from to get our GA just to be the perfect product for you all. And please do complete the session survey in the mobile app that helps us plan a better reInvent for you all next time. Thank you. It's been fun.